Now I'm going to do a video where I show you with Bohr's principle how we work out the total energy of an electron in a hydrogen atom. And once we get that, we can work out where those different lines from the emission spectrum came from. Rydberg, of course, worked it all out just by making numbers up until they fit and came up with his Rydberg constant. But Bohr said, and Einstein thought this was amazing because Einstein thought that you never could mathematically figure all this stuff out. But we do it, and we do it with simple maths in the next video. But for this one, I just want to say that what Bohr was doing was he was basically saying angular momentum, the MVR formula, maybe is related to this constant, Planck's constant. H dash, by the way, is equal to h over 2 pi. We won't go into the difference, but we're saying that n, or an integer number of Planck's constant, will be the way angular momentum works around a, and you see where the 2 pi probably fits in the circle. So we've got this proton, and we've got an electron going around, and he's basically saying, hey, the angular momentum, which for a point rotating about something is equal to mvr, right, equals L, angular momentum. If that's quantized, then that must be equal to h dash for n equals 1, or mvr must be equal to 2h dash for n equals 2, or mvr must be equal to 3h dash for n equals 3. So he's basically saying that this would determine the orbits, and that those jumping levels that we get, or those energy levels that we found, would be related to this angular momentum. And he was totally correct, and we develop it in the next video, where we find out that for this hydrogen atom with its energy levels, in the base state where n equals 1, it has a total energy of 13.6 electron volts. Now, that's our n equals 1 from that Rydberg, and that it will have a different energy at n equals 2, n equals 3, n equals 4, all right? Now, if this is 13.6 electron volts, then we need a formula for figuring out how much energy is up there. And Bohr did that just by making the MVR equal to 2 Planck's constants divided by 2 pi. And his formula came out, basically the way you end up figuring it out is that for n equals 1, you just do 13.6 electron volts divided by 1 squared. That's for n equals 1. For n equals 2, you just do 13.6 electron volts divided by 2 squared, which is 4. And for n equals 3, you just do 13.6 electron volts divided by 3 squared, or 9. That's why these energy gaps are getting smaller and smaller. So as you go up those, you can figure them out. And what you will see in your homework is this formula, which is that E equals HCR all divided by n squared. So if you work out these numbers, they come out the same. It's a negative because the energy is deemed to be, the energy is still, the number is negative because we say that potential energy, when you rip an electron off an atom, if you take it all the way to infinity, then that energy will equal 0. So that's gaining energy to do that. So it must have less energy than 0. And so we give it a negative number. But changes in energy are positive energy. They are not negative energy. This is just where we start our scale, if you like. So when you actually did that calculation with Rydberg for the wavelengths, you could easily have just used these energies, which you can calculate here. Don't forget to put everything back into volts. And if you wanted to get from 2 down to 1, which we know is not going to be visible. The visible ones are the ones that come down to the second line, right? Remember and if you don't know that, you should look at the video. But if we get the energy difference, delta E, between those 2 points, then, and we get that in joules, then we can use this formula to calculate the frequency and thus the wavelength. And it's going to come out the same as that Rydberg formula that you have been using. So there's two angles of attack with this type of problem. There's either use the Rydberg formula, the 1 over wavelength equals brackets, or 1 over wavelength. Let me just write it down. That'll be easier since this is meant to be a video. If I can get my piece of paper. This formula, which you should have seen in the last video, remember, if you were trying to work out between line 2 and line 1, then the series is 1 because you're going from like down to 1, and the line is 2, the second line, and that will give you the wavelength. But you could work out this energy, because this would be 13.6 electron volts. This would be 13.6 electron volts divided by 2 squared, or 4. Get that delta E, subtract them, convert it all into joules, of course, then use that formula, and again you'll get the wavelength. So Bohr was able to calculate those wavelengths just by doing the fact that he was saying angular momentum is equal to n Planck's constants. So he's basically saying that angular momentum came in these packages based on Planck's constant. Quantization, quantum physics.